This is not just another comet story. Tonight, we embark on a gentle but extraordinary journey through the mysteries of this cosmic bullet. You'll hear about its astonishing speed, the strange clues hidden in its icy heart, the puzzling metals in its tail, and the debates stirring among scientists as they look at it and wonder, what exactly are we witnessing? Is this purely a product of cosmic chance, or something more? Let's begin with the most breathtaking fact. This visitor is moving at a speed so extraordinary, it outpaces anything we've ever seen pass through our celestial neighborhood. A guest has burst into our solar system at a tremendous speed. It is 3I Atlas, and it is flying through space at 219,000 kilometers per hour. This isn't just fast, it's cosmically fast. Most comets in our solar system travel at tens of thousands of kilometers per hour. Even the swiftest spacecraft humanity has built can only dream of such velocities. And yet 3I Atlas is moving with the casual confidence of something that has been racing across interstellar space for eons. To understand how astonishing this speed is, picture this. If you could somehow hitch a ride on 3I Atlas, you could travel from Earth to the Moon in less than 2 hours. You would cross the distance between Earth and Mars in less than a day. Even the mighty gravitational pull of the Sun, which binds planets in tight orbits and commands comets to dance around it, is powerless to capture this visitor. The comet streaks through like a stone skipping across a pond, untouched, unstoppable, free. This speed alone tells us something remarkable. Objects that belong to our solar system, asteroids, comets, even spacecraft, are usually bound by the Sun's gravity. They may follow elliptical paths, some elongated, some nearly circular, but they always come back. Their speeds fluctuate as they move closer or farther from the Sun, but ultimately, they are captives in its gravitational embrace. 3I Atlas, however, is different. It is not a captive. Its path through space reveals that it has come from the great beyond, from another star system altogether. It has slipped into our cosmic neighborhood like a stranger passing through a quiet village at midnight, never to return. The sheer velocity of 3I Atlas isn't just a number, it's a story in itself. Speed like this cannot be achieved randomly. It hints at powerful forces in its past, forces that flung it across interstellar space. Before we explore those forces, it's worth pausing to appreciate just how special it is to even see something like this. Our solar system has existed for 4.6 billion years, a span so vast it's almost beyond comprehension. And yet, only a handful of known interstellar visitors have ever been detected. The first was Oumuamua, a mysterious, elongated object that passed by in 2017, leaving scientists puzzled. The second was Comet 2I Borisov, a more typical comet but still from another star. And now 3I Atlas, the fastest of them all, has arrived, streaking through space at 219,000 kilometers h, carrying secrets from the far reaches of the galaxy. Astronomers first spotted it using the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, hence the comet's name. At first, it appeared to be just another faint dot among millions. But as observations accumulated, the numbers began to tell a very different story. Its speed was too high. Its path was too open. Its orbit was not closed like a familiar comet's, but hyperbolic, like the trajectory of a slingshot stone that will never return. In observatories around the world, teams of astronomers leaned closer to their screens. What they were seeing was not a routine discovery. It was a cosmic event. Telescopes swiveled toward the distant visitor. Data poured in. The numbers confirmed it again and again. This was not just any comet. This was the fastest interstellar traveler humanity had ever recorded. This discovery carries a strange emotional weight. To look at something like 3I Atlas is to gaze at a messenger from elsewhere, a wanderer that has crossed unimaginable distances and epochs. Its speed is a kind of signature, a reminder that the galaxy is not static, but alive with motion. Planets orbit, stars drift, galaxies collide, and sometimes, A lonely piece of ice and rock is hurled into the void, destined to pass through alien skies before vanishing back into the dark. Tonight, as you listen and imagine this incredible journey, you can picture 3i Atlas slicing through the vastness like a silent arrow, indifferent to the sun's warmth, untouched by planetary gravity, following a path that was written billions of years ago. The speed of 3i Atlas is not just a spectacular figure in isolation, it's a puzzle piece in a much grander cosmic story. To appreciate what 219,000 kilometers per hour truly means, it helps to imagine the scale of interstellar space. Between the stars, there are no smooth highways, no signposts, no resistance. The comet has been drifting through the galactic night for unimaginable ages, accumulating neither dust nor drag, just continuing its long, straight flight. When it finally entered the outer reaches of our solar system, it didn't accelerate suddenly, it simply arrived, already traveling at tremendous velocity, as if it had been carrying momentum from a distant place, like a whisper carried by the wind across a desert. Astronomers calculate such speeds using precise measurements of position and motion. They track the comet night after night, comparing its position against the fixed background of distant stars. The smallest changes, invisible to the human eye, reveal its trajectory. From these measurements, they deduce how fast it's moving relative to the Sun, Earth, and the broader solar system. When they did this for 3i Atlas, the results startled them. The velocity was not just high, it was hyperbolic, meaning the comet was moving too fast to ever be captured by the Sun's gravity. For comparison, the escape velocity from the solar system at Earth's distance from the Sun is about 42 kilometers per second. 3i Atlas is traveling at over 60 kilometers per second. That difference may seem small, but in celestial mechanics, it's enormous. This extra velocity guarantees that nothing, not even the combined pull of the Sun and the giant planets, can slow it down enough to make it stay. Once it passes through, it's gone forever, on a one-way journey back to the interstellar dark. This kind of speed is rare and special. It's not something that happens to ordinary comets born in our Oort cloud, the distant icy reservoir that surrounds the solar system. Those comets may arrive from great distances, but they are still gravitationally tied to the Sun. They curve inward, loop around, and then return to the distant edges, sometimes taking thousands or even millions of years to complete their orbits. 3i Atlas has no such obligation. Its orbit is not an elongated oval but an open hyperbola. It will not loop back. It will not return. In a way, this speed gives the comet a kind of personality. It feels like a traveler who never stops to rest, someone who moves through places briefly, leaving behind only fleeting impressions before disappearing into the horizon. Unlike planets and comets that belong to our cosmic family, this one is just passing through, unbound by the usual rules. Another way to think of this speed is to imagine the comet's interaction with the solar system as a kind of brief encounter between two moving trains. The solar system itself is orbiting the center of the Milky Way at about 828,000 kilometers h. The comet, coming from another direction, carries its own motion relative to the galactic center. When these two motions meet, the relative speed can be incredibly high, like two vehicles on opposite highways flashing past each other in the night. This is part of why interstellar visitors like 3i Atlas can appear so fast. They're not just moving quickly themselves, but also meeting us in motion. This velocity also makes observing the comet a delicate and time-sensitive task. Astronomers have only a limited window to capture data before it vanishes into the deep sky again. Unlike local comets, which sometimes linger for months or even years, interstellar objects give us only a brief opportunity. Every observation counts. Telescopes around the world are coordinated to track it, gathering light curves, spectra, and images, hoping to learn as much as possible in the short time it remains visible. The comet's extraordinary speed has another implication. It makes it extremely difficult to send any spacecraft to intercept it. To catch something moving at 219,000 kilometers h would require a mission with unprecedented propulsion power and perfect timing. By the time such a mission could be conceived, designed, and launched, 3I Atlas would already be long gone, a vanishing dot against the background of stars. This is why astronomers rely entirely on ground-based and space telescopes to study it. Some researchers have even mused about the poetic sadness of it. To see something so ancient and so fast is to witness a story you can never fully know. The comet comes, it reveals fragments of its nature, and then it leaves again, taking most of its secrets with it. Like finding a single page torn from an ancient book, fluttering through the air, you can read a few lines, but not the whole tale. The speed also helps confirm the comet's interstellar origin. One of the key parameters astronomers use is called the eccentricity of the orbit. If an object has an eccentricity less than 1, it's bound to the Sun. If it's exactly 1, it's on the borderline, following a parabolic escape path. Anything greater than 1 means it's on a hyperbolic trajectory, an interstellar traveler. 3I Atlas has an eccentricity of 6.2, which is staggering. For comparison, the famous Oumuamua had an eccentricity of about 1.2, and that was already enough to mark it as an interstellar object. 6.2 is off the charts. Such an extreme eccentricity reflects its enormous incoming speed. The comet didn't just barely escape the Sun's gravity, it blew past it like a gust of wind past a candle flame. This hyperbolic orbit guarantees that it will not slow down. Once it completes its brief passage through our planetary neighborhood, it will return to interstellar space, likely never encountering another star for millions or even billions of years. When astronomers model its path, they see a graceful curve, a long, sweeping trajectory that enters from the outer dark, bends slightly around the Sun, and then arcs back outward, heading toward the distant stars once again. It's like watching a skipping stone trace a single curve across a still pond. Some like to imagine that 3I Atlas has spent most of its existence in the vast, silent gulfs between stars, where there is no light, no planets, no heat, only endless night and the faint glow of distant galaxies. For perhaps billions of years, it may have wandered through that emptiness, until a chance encounter with our solar system pulled it briefly into view, like a passing lantern glimpsed between trees. Its speed is a kind of fossil record. It contains clues to powerful gravitational events in its past, perhaps a close encounter with a massive planet in its original star system, or the violent turbulence of a galactic merger long ago. These are stories written not in ink, but in velocity and trajectory. By studying the way it moves, scientists are, in a sense, reading that ancient script. This is what makes 3I Atlas such a thrilling and humbling visitor. Its speed is more than just a number, it is evidence of its journey, its origin, and its destiny. And as it races through our skies, we have a fleeting chance to look at it, measure it, and wonder about the long, dark road it has traveled to reach us. When astronomers talk about interstellar speed, they're describing something quite different from what we usually mean by speed here on Earth. On our planet, even the fastest jets are limited by the resistance of air, gravity, and the energy it takes to move through our atmosphere. In space, there's no air, no roads, no obstacles, only gravity and momentum. And in the vast emptiness between stars, speed becomes something almost poetic, a record of ancient forces, a signature of the object's long journey through the galaxy. For most objects in the solar system, their speeds are dictated by their relationship with the Sun. Planets orbit the Sun at specific velocities determined by their distance from it. Mercury rushes around at nearly 48 kilometers per second, while Neptune drifts more slowly at around 5 kilometers per second. Comets coming from the distant Oort cloud can plunge inward at great speeds, but they always remain bound to the Sun, looping through T. Interstellar speed is different. It belongs to objects that are not from here. They don't orbit our Sun. They are merely passing through, their paths shaped by encounters and forces that happen far away, sometimes long before our solar system even existed. When such an object enters our neighborhood, its motion is not defined by our sun's gravity but by its original trajectory through the galaxy. 3I Atlas is a perfect example. Its eccentricity of 6.2 is like a celestial fingerprint, proving its foreign origin. If an object is gravitationally bound to the sun, its eccentricity is less than 1. If it's exactly 1, indicates that this comet isn't merely visiting. It's speeding through on a hyperbolic path that no solar system object could ever naturally follow. This extreme orbit shows that 3I Atlas is moving so fast that the sun's gravitational pull can't slow it down even a little. For comparison, Oumuamua, the first interstellar object we discovered in 2017, had an eccentricity of 1.2. That was already enough to send it back into interstellar space. But 3I Atlas isn't just escaping. It's rushing through like a gust of wind, hardly bending its path at all as it brushes past the sun. Imagine throwing a pebble into a deep well. If you throw it gently, it will fall back down. If you throw it hard enough, it might reach the top, slow down, and then fall back. But if you somehow throw it so fast that it flies straight past the well's edge and into the sky, never to return, that's hyperbolic motion. 3I Atlas is that pebble, hurled with unimaginable force from some distant place in the galaxy. Astronomers use special calculations to describe this. They measure something called the hyperbolic excess velocity, which is the speed the object has after escaping the sun's gravity completely. For interstellar visitors, this number is never zero. It's always some positive value, evidence that they were already moving through the galaxy on their own before they arrived here. For 3I Atlas, this hyperbolic excess velocity is enormous, confirming that it didn't accelerate here, it arrived fast. The Milky Way itself is like a giant cosmic ocean, and stars are like ships drifting through it. Each star has its own velocity as it orbits the galactic center. Our solar system, for example, is moving at roughly 828,000 kilometers per hour around the galaxy. Other stars move in different directions and at different speeds. So when an object like 3I Atlas comes from another star system, its motion relative to us can be incredibly high simply because our ships are moving along different courses. Think of two boats on a vast sea at night. One is moving steadily in one direction. The other is moving just as smoothly in another. When they pass each other, the speed of their encounter isn't the speed of either boat alone but the combined effect of both. That's why interstellar objects can seem to be flying at breathtaking speeds. They're not just fast on their own. They're meeting us while we're also moving. The concept of interstellar speed is also fascinating because it connects local events with galactic dynamics. Every object in interstellar space carries a kind of memory of the gravitational events that launched it. These speeds are often the result of powerful encounters, close brushes with massive planets, gravitational slingshots around stars, or even the violent reshaping of entire star systems. Once set in motion, these objects can travel for billions of years, their speeds slowly changing only as they pass through different gravitational environments. 3I Atlas, with its staggering velocity, likely began its journey ages ago. Long before the first humans looked up at the night sky, before Earth even formed, forces in a distant star system hurled this comet outward. It then traveled through interstellar space, untouched, for billions of years, until one day its trajectory happened to intersect with our own. What we are seeing now is just a brief moment in that incomprehensibly long journey, a blink in the life of the galaxy. There's a strange tranquility in imagining this. While civilizations rise and fall, while continents drift and oceans form, the comet has been moving silently through the void. Its speed is constant, its path determined long ago, unaffected by the dramas unfolding on distant worlds. When we detect it, we are merely intercepting its story mid-sentence. Astronomers are especially excited by objects with such speeds because they offer unique scientific opportunities. By studying their motion precisely, scientists can trace their paths backward through space to estimate where they might have come from. Although pinpointing the exact star system is often impossible, because small uncertainties grow huge over billions of years, it can still reveal valuable clues about the region of the galaxy it originated from. In the case of 3I Atlas, tracing its trajectory backward shows that it likely came from somewhere in the direction of the constellation Lynx, a faint pattern of stars in the northern sky. But because the comet has been traveling for billions of years, the stars themselves have also moved. The galaxy is constantly shifting. So while we can identify a general direction, the comet's true birthplace may now look nothing like it did when the journey began. This is one of the most beautiful aspects of interstellar speed. It connects the past and the present in a single line through space. When we measure the speed and orbit of 3I Atlas, we are effectively glimpsing into a history that stretches back farther than human memory, perhaps even to the early days of the galaxy itself. Some astronomers like to describe these objects as time capsules, drifting through the galactic night. Their speeds are the seals on those capsules, the signatures of the forces that set them free. By studying their motion, we're not just learning about the object itself, we're learning about ancient star systems, long ago planetary dances, and the restless dynamism of the Milky Way. And as 3I Atlas speeds through the solar system, its hyperbolic trajectory reminds us that not everything we see in the sky belongs to us. Some things are just passing through, carrying stories from faraway places, written in the language of speed and distance. The story of interstellar speed doesn't end with a simple number. In truth, each velocity carries within it a long history, almost like a celestial diary. 3I Atlas moves at 219,000 km per hour relative to our Sun, but this is only the speed we measure here and now, from our moving vantage point. To understand its full journey, astronomers have to imagine the galaxy itself as a moving, rotating stage. Everything, stars, comets, clouds of gas, even the spiral arms, drifts and swirls through this grand cosmic ocean. Our solar system is not standing still. It's hurtling around the center of the Milky Way at breathtaking speed, completing a single galactic orbit every 225 to 250 million years. As we travel along this vast trajectory, we occasionally pass through spiral arms, skirt around star-forming regions, and drift through quieter interarm spaces. During this journey, our gravitational field acts like a small eddy in the larger flow. From time to time, objects wandering between the stars cross our path. Some slip through unnoticed. Some burn up in the outer darkness. And some, like 3I Atlas, shine briefly in our skies, leaving astronomers with a fleeting glimpse of their ancient paths. The speed of an interstellar object like 3I Atlas is the result of a complex dance between its original velocity and the motion of our solar system. Astronomers call this relative velocity, and it is one of the most important keys to understanding where these objects come from. It's not just about how fast the comet is moving through space, but also how fast we are moving relative to it. Imagine two trains on parallel tracks, each moving quickly but in opposite directions. To a passenger on one train, the other seems to rush past with incredible speed, even if both are moving at steady, moderate velocities. Similarly, the encounter velocity of interstellar objects depends on the direction and speed of both travelers. The high relative velocity of 3I Atlas tells us that it's not simply drifting gently through space. It's approaching us from a direction that amplifies the. This also helps explain why interstellar objects don't linger. Their paths through the solar system are fleeting intersections of two cosmic trajectories. The comet continues along its ancient course, largely unaffected by the brief encounter. Our Sun's gravity can tug at it slightly, bending its path a little, but not enough to capture it. The result is a graceful hyperbolic curve, like a celestial brushstroke, arcing through our skies before vanishing again into the dark. Some astronomers like to describe this moment as two travelers meeting briefly at a cosmic crossroads. For a short while, their paths align, they share a silent moment under the stars, and then they move on, each following their own journey. It's a poetic way of seeing what is, at its heart, a mathematical interaction between two gravitational systems. To calculate these trajectories, scientists rely on incredibly precise observations. Even tiny errors in measurement can lead to huge differences in predictions when you're dealing with billions of kilometers and hyperbolic paths. Modern telescopes track the comet night after night, comparing its position against distant background stars. Sophisticated software then fits these observations to orbital models, slowly refining the shape of its path through the solar system. For 3I Atlas, this work revealed that its trajectory is steeply hyperbolic, with an eccentricity of 6.2, far beyond the limit for bound orbits. This tells us not only that it's from outside the solar system, but that it's traveling on a trajectory that's almost straight compared to the curved orbits of local comets. It barely bends as it swings around the Sun. Such a shape is unique to objects arriving from interstellar space. The moment astronomers confirmed this, the excitement grew. Each interstellar visitor is like a rare messenger. We don't control when they arrive. We can't predict them far in advance. We simply notice them, sometimes almost by chance, and then the race begins to collect as much data as possible before they disappear again. The concept of interstellar speed also touches on galactic dynamics in a profound way. The Milky Way is filled with billions of stars, each with its own planets, asteroids, and comets. Occasionally, gravitational interactions, especially near massive planets, can fling smaller bodies out of their star systems entirely. Once free, these objects drift through the galaxy at the velocities they had when they escaped, modified by encounters with other gravitational fields over time. Picture countless tiny ice grains and rocky fragments wandering through the darkness between stars. Some have been traveling like this for longer than Earth has existed. They pass through regions of star formation, weave between nebulae, and glide through spiral arms, carrying with them the faint chemical signatures of the environments they once knew. Their speeds are like notes in a cosmic symphony, each one shaped by different gravitational instruments. For scientists, the hyperbolic trajectory of 3I Atlas isn't just a curiosity, it's a clue. By tracing the comet's path backward through space, they can make educated guesses about the direction it came from. In the case of this comet, the backward projection points roughly toward the constellation Lynx. But because billions of years may have passed since it left its home system, the stars in that region have long since moved. The galaxy is in constant motion. Nothing stays where it was. So, the comet's birthplace may now be unrecognizable. Still, these calculations are valuable. They provide hints about the kinds of star systems that might have launched such a fast traveler. Was it ejected by a giant planet in a system like our own? Was it caught up in the gravitational chaos of a young, crowded star cluster? Or did it emerge from a region shaped by even larger forces, like galactic tides or the disturbances of passing stars? Each possibility carries different signatures in the comet's speed and trajectory. The very idea of interstellar speed reminds us that our solar system is not isolated. We are part of a dynamic, interconnected galaxy where objects and energy flow between stars over immense timescales. 3I Atlas is not unique because it's fast. It's special because we noticed it. For every one of these travelers that we detect, countless others may pass through unnoticed, faint and silent, slipping between the watchful eyes of telescopes. Somewhere out there, beyond the range of our instruments, other ancient travelers may be drifting by right now, unseen, untouched, each carrying its own story written in speed and distance. Perhaps some pass close to other stars, perhaps some wander for eternity, and perhaps a few will someday find themselves drawn into new systems, becoming part of new cosmic families. Interstellar speed is both a scientific concept and a reminder of our cosmic context. These velocities link distant regions of the galaxy, connecting the past with the present, and reminding us that even in the vastness of space, paths sometimes cross in the most unexpected ways. As 3I Atlas continues its high-speed journey, its brief visit leaves astronomers with more than just data. It leaves them with a renewed sense of wonder about the restless, ever-changing galaxy we inhabit. For a short time, we are witnesses to its flight, watching a silent messenger race through the night, carrying secrets from a place we may never see. The speed of 3I Atlas is not just a spectacle, it is a mystery. To travel through space at more than 219,000 kilometers per hour is to carry with you the signature of some powerful past event. Objects do not simply acquire such velocities by drifting gently away from their star systems. They must be pushed, pulled, or flung by immense gravitational forces, set upon a course that will carry them far from home for billions of years. Astronomers have proposed several theories about how this could happen, each one like a different chapter in the comet's unseen history. One of the most straightforward explanations involves giant planets. In many planetary systems, massive gas giants orbit their stars, colossal worlds like Jupiter and Saturn in our own solar system, or even larger ones known as superjupiters in other star systems. These giants exert tremendous gravitational influence on their surroundings. If a smaller object, like a comet or icy body, strays too close, it can be flung outward like a stone launched from a slingshot. In our solar system, Jupiter is the great architect of such gravitational encounters. Over the billions of years of its existence, Jupiter has scattered countless comets, asteroids, and fragments, some inward toward the inner planets, others outward toward the distant Oort cloud. In rare cases, if the timing and trajectory are just right, an object can receive enough energy from a close encounter to escape the Sun's gravity altogether. This is called a gravitational ejection. The same principle applies in other star systems. If 3I Atlas once orbited a distant star with a giant planet, a close pass near that massive world could have flung it outward at high speed, sending it on a journey into interstellar space. Over time, the gravitational influence of the original star would fade as the comet moved farther away, and the object would be left to drift through the galaxy on its own. Astronomers often picture this as a kind of celestial billiard game. A small ball, our comet, rolls toward a much larger ball, representing the giant planet. The gravitational pull bends the small ball's path sharply, redirecting it with increased speed, sending it ricocheting out of the system. It's a silent, invisible interaction, but the result is dramatic, a tiny object hurled into the darkness, never to return. Another, even more powerful scenario involves regions of space where stars are densely packed together, stellar nurseries and clusters. In these crowded environments, stars often pass very close to one another. Their gravitational fields interact, disturbing the orbits of planets and smaller objects around them. These chaotic interactions can lead to sudden and violent ejections. A comet like 3I Atlas could have been swept out of its original system by a passing star's gravity, receiving an enormous velocity boost in the process. Young star clusters are particularly chaotic. Stars are born close together from the same cloud of gas, and in their early lives, they often approach one another closely before drifting apart. During this time, planetary systems are still forming and stabilizing. This makes it easy for small icy bodies to be perturbed and ejected into interstellar space. If 3I Atlas originated in such an environment, it might have been launched on its journey in the earliest epochs of its star system's life, possibly more than 7 to 14 billion years ago, if current age estimates are correct. Imagine a young galaxy, alive with stellar birth and chaos. Clusters of newborn stars flicker like campfires scattered across the galactic plane. In these crowded nurseries, gravitational forces tug and pull like invisible hands, rearranging planets and comets with careless ease. It was in such a place, perhaps, that a small icy traveler was sent flying outward, its future already determined in a single, fateful encounter. But there is another, more dramatic possibility: galaxy-scale events. Our Milky Way has not always been a quiet spiral drifting through space. Over billions of years, it has collided and merged with smaller galaxies, absorbing them in titanic gravitational encounters. These galactic mergers unleash tremendous forces, reshaping stellar orbits and scattering material across interstellar space. A comet caught up in such an event could be accelerated to immense speeds, far beyond what a single planet or star could impart. During these mergers, tidal forces stretch and distort galaxies like cosmic taffy. Streams of stars and gas are torn free and flung outward into space. Entire planetary systems can be displaced. A comet that once orbited a star peacefully might suddenly find itself swept along by these vast gravitational tides, gaining enormous speed as it's pulled and pushed by the shifting mass of billions of stars. This scenario is especially intriguing when scientists consider the estimated age of 3I Atlas. If the comet truly is between 7 and 14 billion years old, it may have originated in a very early chapter of galactic history, perhaps during one of these major merger events. Back then, the galaxy was a far more tumultuous place, with frequent collisions and intense star formation. Picture colossal rivers of stars colliding, their light blending like streams of molten gold. Somewhere in that chaos, a comet is swept along, gaining momentum not from a single planetary encounter, but from the collective gravitational pull of entire star systems. It is flung outward, away from the merging galaxies, into the quiet night between the stars. It will drift there for eons, its icy surface unchanged, carrying the memory of that ancient upheaval in the form of its speed. There's also the possibility of encounters with massive compact objects, black holes. The gravitational fields around black holes are extreme. If a comet passed near such an object without being destroyed, the gravitational slingshot effect could accelerate it to incredible velocities. Although this is a rarer scenario, it's theoretically possible. Black holes, especially those lurking in dense stellar regions or at the centers of galaxies, can impart extraordinary speeds to passing objects. The fact that 3I Atlas has such an unusually high eccentricity and velocity compared to previous interstellar visitors like Oumuamua or 2I Borisov suggests that it may have undergone a particularly energetic ejection event. It's not just a wanderer, it's a bullet, launched long ago by some powerful gravitational gun. For astronomers, these theories are not mere speculation. They are tools for understanding the broader processes that shape galaxies and planetary systems. By studying 3I Atlas, they're not only learning about one comet, but about the gravitational dramas that unfold across the cosmos, often unseen and over unimaginable timescales. There's a quiet thrill in this kind of detective work. Each theory is like a different pathway into the past, a way of imagining the comet's life before it crossed our skies. Was it a quiet ejection by a distant planet? A chaotic shove from a passing star? A catapult launched during the merging of galaxies? Or a slingshot around a dark, invisible monster at the heart of a star cluster? We may never know for certain. But the comet's speed is a clue, a breadcrumb left on the cosmic trail. What's certain is that the forces required to give a small object such velocity are immense, far beyond anything humanity can currently create. They speak of a galaxy alive with motion, a place where stars, planets, and comets are constantly interacting, sometimes gently, sometimes violently, shaping the paths of travelers like 3I Atlas for billions of years to come. Time moves differently in space. Here on Earth, we measure time in seconds, years, and lifetimes. But for an object like 3I Atlas, time is measured in billions of years, in the slow rhythm of galactic evolution. This comet has traveled for so long that its very existence is like a whisper from the dawn of the Milky Way. When astronomers look at it, they are not merely seeing a chunk of ice and rock. They are gazing at a time capsule, a piece of ancient history still gliding silently between the stars. The estimated age of 3I Atlas ranges between 7 and 14 billion years. That number is staggering. Our own solar system is about 4.6 billion years old, already an immense stretch of time, but 3I Atlas may predate it by billions of years. If these estimates are correct, then this comet was already ancient when the Sun was born. It has witnessed cosmic events that no living creature could imagine. Scientists calculate such ages not by reading a clock, but by examining composition, dynamics, and galactic models. The comet's structure and trajectory hold subtle clues about its origin. Interstellar comets are not like the ones that orbit the Sun in predictable ellipses. They come from elsewhere, and their materials have been preserved in cold, deep space for eons. Unlike comets that have made repeated close passes to a star, interstellar objects often retain their primordial structure, essentially unchanged since their formation. Think of a fossil buried deep underground. Over millions of years, it remains untouched, shielded from erosion and weathering. When it is finally uncovered, it reveals a snapshot of life long past. Similarly, a comet drifting through the emptiness between stars is preserved in a kind of cosmic freezer, its surface unchanged, its interior untouched by heat or radiation. If 3I Atlas truly formed 7 to 14 billion years ago, then its birthplace may have been a very different galaxy from the one we know today. Early in the history of the universe, stars were forming rapidly, but heavy elements like iron, nickel, and carbon were scarce. The first generations of stars were massive and short-lived, forging elements in their cores and scattering them when they died in supernova explosions. The debris from these ancient stars seeded the cosmos with the raw material for later generations of stars and planets. Imagine that distant era, a young galaxy, darker and rougher than the graceful spiral we inhabit now. The stars were bluer and hotter. There were no planets like Earth, no calm solar systems, only storms of gas and clouds of dust swirling under newborn starlight. In one of those clouds, tiny grains of ice and rock began to stick together. Over time, they formed a comet, small, fragile, and new. This was the beginning of 3I Atlas's journey. As stars lived and died, as galaxies collided and merged, this comet was likely ejected from its home and cast into the galactic void. For billions of years, it has traveled through interstellar space, untouched by sunlight, perhaps passing near other stars but never captured. It has drifted through regions of darkness and silence so complete that human imagination struggles to picture them. No planets, no atmospheres, no light, only the faint glow of distant galaxies, like a backdrop painted on the walls of infinity. Age, in this case, is not just a number. It's a story of survival. For a fragile object to exist for billions of years without disintegrating or being destroyed is remarkable. Comets can be easily torn apart by gravitational encounters, evaporated by starlight, or shattered by collisions. 3I Atlas has avoided all of these fates. It has survived galactic mergers, stellar births, supernova shockwaves, and cosmic radiation. It has kept going, like a silent witness to cosmic history. Picture it gliding through the darkness, orbit after orbit, age after age, as entire civilizations rise and fall on countless worlds it will never visit. It has no awareness, no destination. It is simply there, carried along by the great rivers of gravity that flow through the galaxy. It has seen the Milky Way change shape. It may have passed near stars that are long dead, through nebulae that have dispersed, and alongside worlds that formed and perished before our sun was born. The estimated age range also hints at something profound. 3I Atlas may not even be native to our galaxy in its current form. If it is closer to 14 billion years old, that would place its origin around the time when the universe itself was young, not long after the Big Bang. The Milky Way was still assembling from smaller protogalaxies back then. This comet may have been born in one of those small, ancient star systems that were later absorbed by the growing Milky Way. In this sense, 3I Atlas is more than a visitor, it is a messenger from a lost world. The star system that gave birth to it may no longer exist. Its sun may have burned out long ago, or been torn apart during galactic mergers. Yet this one small object remains, carrying the chemical fingerprints of its birthplace like a message sealed in ice. For astronomers, this makes 3I Atlas invaluable. By studying its composition, scientists can learn about the conditions that prevailed in the early galaxy. They can compare it to younger comets from our own solar system to see how the raw materials of planets and stars have evolved over time. In this way, 3i Atlas is like a wandering laboratory, offering insights into epochs we can never directly observe. It's almost poetic to think that as we point telescopes toward it, trying to decipher its secrets, this comet has existed for longer than our species, our planet, and even our sun. It has traveled patiently across time, waiting for a civilization to appear that could finally notice it. And now, for a brief moment, our paths have crossed. For billions of years, 3i Atlas wandered unseen, and now, at last, a tiny world on the edge of a spiral galaxy is watching. It doesn't change the comet's journey. It will continue unaffected, but for us, this encounter is extraordinary. We are witnessing something truly ancient, something that connects us to the earliest chapters of the universe itself. In the quiet of the night sky, if you imagine this comet sailing through space, you might picture it like a lantern drifting across a dark ocean. It is small, cold, and silent, but its light is history itself. And though we cannot hear it, its long journey speaks of endurance, change, and the vastness of cosmic time. For billions of years, 3i Atlas wandered silently through interstellar space, unchanged and unnoticed. But when it finally approached our solar system, astronomers turned their most powerful instruments toward it, and what they discovered in its tail left them astonished. It wasn't just ice and dust trailing behind this ancient traveler. It wasn't just frozen gases evaporating under sunlight, as is common with most comets. Within that delicate, shimmering tail, scientists detected something unexpected: nickel and iron atoms, floating freely in space. At first glance, this might not seem unusual. After all, nickel and iron are common elements in the universe. They're found in planets, asteroids, meteorites, and even in the cores of stars. But here's the mystery. The comet was too far from the sun, and the temperature around it was too low to vaporize such heavy metals. At those distances, the environment is frigid, far below the temperatures needed to turn nickel and iron into gas. By all standard models, they simply shouldn't be there. To understand why this is so strange, imagine holding a piece of solid metal in your hand on a freezing winter day. The cold is so intense that even the warmest breath won't melt it. That's how these metals behave in space. In the outer regions of a solar system or the depths of interstellar space, they remain solid, locked inside the body of a comet or asteroid. They do not simply drift away as vapor. And yet, in the case of 3i Atlas, they were there, detectable, floating in its coma like a silent signature. This discovery puzzled scientists because similar findings had only recently been made for a few comets within our own solar system, and even then, the presence of vaporized nickel and iron at low temperatures had challenged existing cometary models. For a distant interstellar comet to show the same phenomenon suggests something unusual about its composition or its internal structure. One possible explanation is that the metals are being released from the surface through sublimation of unusual compounds, perhaps nickel or iron-bearing molecules that can break down and free metal atoms even at low temperatures. If the comet formed in a region rich in these exotic compounds, its tail could naturally contain metals under conditions that would normally seem too cold. Another hypothesis focuses on the comet's structure itself. Over billions of years drifting in space, the outer layers of the comet may have become porous, fragile, and riddled with microfractures. When sunlight finally touched its surface again after eons, even weak heating could cause sudden breakouts of trapped gases, carrying microscopic grains of metal with them into space. These grains could then be broken down into individual atoms by solar radiation, producing the observed nickel and iron signatures. It's like a frozen sponge that has been left untouched for ages. When it finally thaws, even a little warmth can cause trapped air and water to burst out suddenly through tiny holes, carrying with them whatever was locked inside. In the same way, The ancient crust of 3I Atlas might be venting its long-hidden materials as it approaches the warmth of our Sun. But there's another layer to this mystery. The ratio of nickel to iron observed in the comet's gas tail is unusual. It closely resembles the ratio found in some industrial alloys or certain types of meteorites forged under extreme conditions. This is what drew the attention of Harvard astrophysicist Avi Loeb, who suggested that perhaps something even stranger was at play. Loeb asked a provocative question: what if the metals were not produced naturally at all? What if their presence, and their precise ratio, hinted at an artificial origin? After all, if standard cometary processes cannot explain the vaporization of nickel and iron at low temperatures, perhaps there's another explanation, one involving technology or engineered material. To be clear, Loeb didn't claim that 3I Atlas is definitively artificial. But he raised the possibility that this comet could be a fragment of something created by an advanced civilization long ago, or even a piece of debris from a technological structure. He noted that the observed metal ratios are similar to those used in some high-performance alloys on Earth, which immediately set off debates across the scientific community. Many astronomers responded cautiously, pointing out that there could be exotic but natural processes we have not yet fully understood. Interstellar objects may form in environments very different from our solar system, and their chemistry might surprise us. Others, however, found the idea worth investigating. After all, the discovery of Oumuamua had already challenged many expectations, and 3I Atlas is proving to be even stranger. Imagine for a moment that this ancient traveler carries not just the frozen memory of distant star systems, but the fingerprints of technology, not in the form of blinking lights or metal plates, but hidden in the ratios of elements in its tail. If that were true, this would be one of the oldest and most enigmatic artifacts in the galaxy, drifting silently for billions of years before brushing past our Sun. Even if the explanation turns out to be entirely natural, the mystery of the nickel and iron tells us something profound. There are still processes in space that we do not fully understand. Comets, once considered simple balls of ice and dust, are revealing themselves to be far more complex, with intricate chemistries and structures shaped by their long histories. The discovery has spurred intense observational campaigns. Telescopes on Earth and in orbit have begun to study the tail of 3I Atlas in greater detail, trying to determine the exact mechanisms releasing these metals. The answers could reshape our understanding of cometary physics, and perhaps even of interstellar material itself. For now, the image is quietly poetic. A lonely comet drifting through space, trailing behind it a faint glimmer of nickel and iron. These atoms, forged long ago in the hearts of stars, have waited billions of years to shine briefly in the light of a new sun. Whether their story is natural or artificial, it is undeniably ancient and undeniably beautiful. As night falls on Earth, somewhere in the darkness beyond the Sun, 3I Atlas continues its journey. Its tail stretches into space like a delicate thread, glimmering faintly with metals that shouldn't be there. And as scientists puzzle over their instruments and data, the comet remains silent, offering no easy answers, only more questions carried on a trail of shining mystery. The comet's tail, delicate and ghostly, is more than just a stream of frozen gases. It is a kind of cosmic diary, recording not only the materials that make up the object but also the processes that have shaped it. For most comets, what evaporates into space is predictable: water ice, carbon compounds, simple molecules that sublimate easily under the faint touch of sunlight. But 3I Atlas refuses to follow the script. The presence of vaporized nickel and iron in its tail suggests that something about this comet is different. Something buried in its structure or history has allowed these stubborn metals to escape into space. One idea gaining attention among researchers is that the metals may not have come directly from vaporization, but from the breakdown of unusual compounds locked in the comet's body. Over billions of years in interstellar space, the surface of 3I Atlas may have undergone subtle chemical changes, slowly transforming as cosmic rays and micrometeorites bombarded it. In this long, cold exile, metals and ices could have formed complex structures, some of which may release nickel and iron atoms when gently warmed, even at low temperatures. Another possibility is that the comet's outer shell is far more fragile and porous than expected. Imagine a surface riddled with tiny cracks, voids, and passages, a structure that has been weathered not by wind and rain, but by cosmic radiation and the passage of unimaginable time. When the comet finally approached the Sun after eons of darkness, even a slight increase in temperature could have triggered sudden outgassing. Jets of trapped material might have burst through these microfractures, carrying metal grains with them into the surrounding coma. Solar radiation, ever relentless, would then break these grains down further, freeing individual atoms into space. This idea of slow venting fits the observations well. The nickel and iron were not detected as chunks of metal, but as individual atoms spread through the coma. This suggests a gradual, continuous process, rather than a violent event. It's as if the comet, long frozen and silent, had begun to breathe again, exhaling traces of its interior into the sunlight. The ratio of nickel to iron in these emissions is particularly intriguing. It doesn't match what scientists typically observe in comets from our own solar system. Instead, it points to formation conditions that may have been very different, perhaps in a colder region, or in a part of a distant star system with unique chemical properties. This raises important questions about the environment in which 3I Atlas was born. If these ratios reflect its birthplace, then the comet is offering us a rare glimpse into a distant and ancient star system. Its metals carry the imprint of that environment, like a geological signature preserved in ice. By comparing these ratios to those found in meteorites, planets, and other comets, astronomers can begin to reconstruct the conditions of its origin. The mystery deepens when considering the comet's age. If 3I Atlas truly formed billions of years ago, the chemical fingerprints in its tail may come from a period of cosmic history when galaxies were younger and heavier elements were less abundant. The presence of nickel and iron might indicate that the comet formed near a massive, metal-rich star, or in the debris of ancient stellar explosions that enriched its surroundings with heavy elements. It's also possible that the comet has preserved materials from more than one environment. Over time, as it drifted through different regions of the galaxy, its surface may have accumulated layers from various encounters. Each layer would carry its own chemical history, building a complex record of cosmic travel. When sunlight began to warm it again, all of these layers would contribute to the strange mix of emissions we observe today. Whatever the explanation, this discovery has changed the way scientists think about comets, especially those arriving from interstellar space. These are not simple objects frozen in time. They are complex, evolving bodies that hold the stories of the galaxy within their fragile shells. Nickel and iron, usually hidden away in the hearts of stars or deep within planets, are now appearing in the cold, quiet tails of comets, reminding us that the universe is always capable of surprises. There is a quiet beauty in this puzzle. A lone traveler, older than our solar system, glides through space, trailing behind it the faintest glimmer of metals forged long ago. These atoms have been waiting in darkness for billions of years, locked away until the moment the comet wandered close enough to a star to release them. As they catch the sunlight, they reveal secrets that no telescope could have guessed on its own. Some mysteries arrive not as loud revelations, but as gentle, persistent questions. The nickel and iron in the tail of 3I Atlas are such questions. They ask us to look deeper, to think beyond what we expect, and to remember that even the smallest details can carry the weight of cosmic history. Sometimes, a mystery in science grows so large that conventional explanations begin to feel like patchwork, plausible but incomplete, like trying to describe an entire landscape by only looking at a single tree. The strange behavior of 3I Atlas, especially the presence of nickel and iron in its tail, and its extraordinary speed, has pushed some scientists to ask deeper, more daring questions. Among them is Avi Loeb, an astrophysicist at Harvard University known for his willingness to consider possibilities that others might overlook. Loeb is no stranger to controversy. He has spent much of his career studying black holes, galaxies, and the origins of cosmic structures, but he also became widely known when he suggested that the first interstellar visitor we detected, Oumuamua, might not be a natural object at all. He argued that its unusual shape, lack of a visible coma, and odd acceleration could be consistent with a piece of alien technology, perhaps a fragment of a light sail or debris from a long-vanished civilization. While many disagreed, his arguments sparked widespread debate and renewed interest in looking at interstellar objects with fresh eyes. So when 3I Atlas appeared, moving even faster and displaying chemical signatures that didn't fit neatly into existing cometary models, it was perhaps inevitable that Loeb would turn his attention to it. His interest centered not only on the comet's astonishing eccentricity and speed, but also on the ratio of nickel to iron found in its gas tail. This ratio, surprisingly, resembles that found in certain high-performance alloys, materials that on Earth are often created intentionally for technological purposes. Loeb raised a simple but provocative question: what if this comet, or at least part of it, is not entirely natural? What if, somewhere in its ancient history, this object was once part of something engineered? To be clear, Loeb did not claim that 3I Atlas is definitively an alien spacecraft or probe. His approach is more careful than that. He suggested that, given the unexplained anomalies, it would be unscientific not to consider all possibilities, including the technological. In his view, the greatest mistake humanity can make when studying the universe is to assume that everything must fit our existing categories. He pointed out that 3I Atlas is unusually large for an interstellar visitor. If it were a typical natural object, we should statistically have detected thousands of smaller interstellar comets and asteroids before finding something this big. Instead, the opposite happened. We saw Oumuamua first, a small, mysterious body, and then 3I Atlas, which is significantly larger and faster. This statistical oddity suggests that either our detection methods are still missing countless small objects, or that 3I Atlas might not belong to the same population we expected. The nickel-to-iron ratio added another layer of intrigue. On Earth, these elements are often combined in specific ways to produce alloys with desirable properties: resistance to heat, strength, or durability in extreme conditions. Finding a similar ratio in the tail of a distant comet doesn't automatically prove anything, but it is unexpected. Loeb argued that if natural explanations continue to fall short, we must be willing to at least entertain the idea that the material could have artificial origins. This line of thinking leads to fascinating possibilities. Perhaps 3I Atlas is the shattered remnant of a technological structure from a civilization that existed billions of years ago. Maybe it is a fragment of a long-lost megastructure, cast out into interstellar space by some ancient catastrophe. Or it could be debris from a probe or ship that ventured too close to a star and was torn apart, its pieces scattered into the galaxy. Over billions of years, those fragments could have weathered down until they resembled comets, their origins hidden beneath layers of ice and dust. These scenarios may sound like science fiction, but Loeb's argument is not about proving that one of them is true. It is about remaining open to evidence, especially when faced with anomalies that don't fit standard models. History has shown that scientific breakthroughs often come when someone dares to ask questions that others are reluctant to pose. Loeb's ideas have, unsurprisingly, met with skepticism. Many astronomers prefer to focus on natural explanations, pointing out that our understanding of interstellar chemistry and cometary physics is still in its early stages. They argue that the unusual metal ratios may simply reflect unfamiliar formation environments, not alien technology. Interstellar space is vast, and the variety of star systems within the galaxy is immense. It's possible that 3I Atlas was born in a place unlike anything near our Sun, where these ratios occur naturally. Yet even these critics acknowledge that Loeb's approach has value. By encouraging scientists to consider a broader range of hypotheses, he ensures that unusual data are not ignored or prematurely dismissed. His work pushes the boundaries of curiosity, reminding the scientific community that the universe is full of surprises, and that our assumptions, while useful, are not absolute truths. The idea that 3i Atlas might have a technological component is not about proving alien life tomorrow. It is about keeping the door open. If civilizations have risen and fallen over the course of billions of years, as is entirely plausible in a galaxy this old, then the debris of their existence could still be drifting through space, indistinguishable at first glance from natural objects. If we don't look closely, we might never notice. In a way, this perspective adds a poetic dimension to the comet's story. Imagine a fragment of something ancient and intelligent, wandering silently through the galaxy for eons, passing countless stars and worlds, never noticed until one small planet with telescopes finally catches sight of it. Even if the reality is far more mundane, that possibility alone expands the horizon of our imagination. As telescopes continue to study 3i Atlas, scientists will look for more clues: its composition, its structure, its behavior under sunlight. Each new piece of data helps to narrow down the possibilities. Whether the explanation is exotic chemistry, unusual formation conditions, or something truly extraordinary, the mystery drives us forward. And in the quiet night sky, far from the noise of human debate, the comet itself continues on its trajectory, indifferent to the questions it inspires. It is neither trying to reveal secrets nor to keep them. It simply is, gliding through the galaxy as it has for billions of years, leaving us to wonder what stories are hidden in its ancient heart. When Avi Loeb's comments about 3i Atlas began to circulate in academic circles, the reaction was immediate and mixed. Some scientists admired his courage to challenge conventional thinking. Others worried that such speculation could distract from more grounded research. Yet whether people agreed with him or not, his ideas had done something remarkable. They had forced everyone to look at this comet more closely, to ask sharper questions, to push beyond the comfortable boundaries of existing models. In a sense, this is how science grows. A mystery appears, and while most researchers focus on explaining it within known frameworks, a few step to the side and ask, "But what if we're missing something entirely?" Loeb plays that role. He is not always right, and he knows it, but his willingness to entertain extraordinary possibilities ensures that anomalies like 3i Atlas are not quietly swept aside as statistical outliers. Instead, they become focal points for intense investigation. The possibility that 3i Atlas could be artificial, or at least partially artificial, remains speculative, but even speculation can be productive. It inspires new ways of analyzing data. For example, astronomers began looking more carefully at the light curve of 3i Atlas, the subtle variations in brightness that can reveal an object's shape, rotation, and structure. If it were a fragment of technology, one might expect unusual reflective properties or regular patterns that hint at structured surfaces rather than random rocky or icy features. These kinds of analyses require patience and precision, often stretching over months, but they can reveal extraordinary details from light alone. The comet's trajectory was also examined for hints of non-gravitational acceleration, as was seen with Oumuamua. In that case, the object seemed to speed up slightly as it left the solar system, possibly due to outgassing, but some argued that the effect was too smooth to be explained that way. If 3i Atlas displayed a similar effect, it might indicate jets of gas escaping unevenly, or, in a more speculative sense, some other kind of propulsion. So far, observations have shown no obvious anomalies in its motion, but the data collection continues, especially as it re-emerges from behind the Sun later in the year. Loeb's team also suggested that future missions could aim to intercept interstellar objects like 3i Atlas. This idea, once considered far-fetched, is gaining traction. Several space agencies are studying the feasibility of rapid response missions that could launch a spacecraft to study an incoming interstellar visitor up close. If we ever manage to send a probe to intercept one of these objects, we could finally determine their true nature, not just from the light they reflect, but by examining their surface and composition directly. For now, though, 3I Atlas remains too vast and distant for such a mission. It is a fleeting visitor, here for a moment, then gone forever. Still, even without a physical mission, Earth's most powerful telescopes can glean extraordinary information. The James Webb Space Telescope, with its infrared capabilities, can detect subtle signatures in the dust and gas surrounding the comet. Spectroscopic analysis can reveal the presence of unexpected compounds, unusual ratios of elements, or structures in the tail that might hint at something beyond ordinary cometary behavior. Every new observation is like another brushstroke on the portrait of this mysterious traveler. Beyond the technical aspects, Loeb's theory touches something deeper in the human imagination. For centuries, people have looked at comets with a mixture of awe and fear. In ancient times, they were seen as omens, harbingers of change, symbols of distant realms. In the modern era, they have become scientific puzzles, windows into the early solar system. But interstellar comets like 3I Atlas add a new layer. They are not just relics of our own cosmic neighborhood, but messengers from other star systems. They carry with them the chemistry, history, and perhaps even the secrets of places far beyond our own. The thought that one of them could bear traces of intelligent activity transforms that sense of awe into something even more profound. It also raises practical questions about how humanity would respond if evidence of technology were ever found on such an object. What if, in the tail of a comet like 3I Atlas, we detected unmistakable signatures of artificial material, something that nature could not produce? How would our world react? Would scientists argue endlessly over interpretation? Would governments rush to claim the discovery? Would humanity come together in shared wonder, or splinter into competing factions? These questions remain hypothetical, but they remind us that cosmic discoveries have real consequences for how we see ourselves. Loeb argues that the best approach is to be prepared, not in the sense of building spaceships, but in building scientific and cultural readiness. If we remain open-minded, methodical, and curious, we will be better equipped to interpret whatever we find without leaping to conclusions or retreating into denial. For him, 3I Atlas is not just a comet, it is a test of our willingness to explore possibilities with both rigor and imagination. Interestingly, even critics of Loeb's views admit that such thinking has benefits. By proposing technological explanations, even if they are ultimately proven wrong, researchers are pushed to refine natural models more carefully. For example, when Loeb suggested that Oumuamua might be artificial, other teams developed more sophisticated cometary models to explain its acceleration without invoking technology. This led to new insights into how cometary outgassing might behave in unexpected conditions. In this way, bold ideas act as catalysts, accelerating scientific progress in directions that might otherwise have been neglected. And so, 3I Atlas becomes more than just a fast-moving ice and rock object. It becomes a mirror, reflecting not only the light of the sun but also the curiosity and boldness of the human mind. The debates around it highlight the diversity of scientific thought, cautious observers, daring theorists, data analysts, mission planners, all contributing different pieces to the puzzle. The comet itself remains silent, indifferent to these discussions, gliding through the darkness as it has for billions of years. But in its silence, it inspires a symphony of thought back on Earth. As night falls and telescopes turn toward the sky, scientists continue their patient watch. Some hope for a clue hidden in the data that will settle the debate. Others are content simply to observe, knowing that even unanswered questions have value. And among them, Avi Loeb remains a persistent voice, reminding the world that sometimes the universe whispers secrets we can only hear if we are willing to listen with open minds. Somewhere out there, beyond the faint halo of the sun, 3i Atlas sails on. Perhaps it carries nothing more than dust, ice, and ancient metal. Or perhaps, embedded deep within its frozen heart, lies a story older and stranger than we can yet imagine. Whatever the truth, its passage through our skies has already left a mark, not on the heavens, but on us. Whenever a mysterious discovery captures the world's attention, the next phase is almost always the same. After the first wave of excitement and speculation comes the careful, methodical work of scientists who try to fit the new data into the broader framework of what we know. This is the stage where bold claims are tested, uncertainties are narrowed, and the extraordinary is weighed against the ordinary. In the case of 3i Atlas, this critical phase has been both fascinating and revealing. Many astronomers have pointed out that, before we jump to conclusions about artificial origins or unprecedented cosmic events, we should first examine whether natural explanations can account for the comet's strange characteristics. After all, the galaxy is vast, and the diversity of objects it contains is almost beyond imagination. Just because something is unusual to us does not mean it is unique to the cosmos. Sometimes, anomalies arise not because nature is being strange, but because our sample size is still small. The first major point of debate centers on statistics. Interstellar objects are rare visitors to our solar system, at least from our current observational perspective. Oumuamua was the first confirmed example, discovered in 2017. It was small, faint, and passed by quickly. Then came Borisov, the first interstellar comet, a more typical icy body. And now 3i Atlas, the fastest and most eccentric of them all. If these objects were truly common, we should expect to have seen many smaller examples by now. The fact that one of the largest and fastest objects was detected so early raises interesting statistical questions. Some scientists argue that this may simply reflect detection bias. Large, bright objects like 3i Atlas are easier to spot from Earth, especially with the telescopes currently in use. Smaller objects could be passing through the solar system unnoticed every year, their brief appearances too faint to trigger detection algorithms. As survey technology improves, particularly with upcoming observatories like the Vera Rubin Observatory, we may find that interstellar visitors are far more common than we think. In this view, 3i Atlas is not necessarily exceptional. We are simply at the beginning of a new era of discovery. Others, however, suggest that the detection of such an object so soon after the first known interstellar visitor hints at something deeper. Perhaps the population of large, fast-moving interstellar objects is more significant than models predict. If so, this would challenge existing ideas about how material is ejected from planetary systems and how it travels through the galaxy. Traditional models suggest that most ejected materials should be relatively small, cometary fragments, debris, and rocks. Large intact bodies like 3i Atlas should be rarer. This leads to the second major area of debate: formation and ejection mechanisms. Theories about how interstellar objects achieve their high velocities typically involve gravitational interactions with massive planets or extreme events like close encounters with black holes or passing stars. If 3i Atlas is part of a population of similarly fast and large objects, then either these mechanisms are more common than previously believed, or there are other, as yet unknown processes at work. Critics of technological hypotheses emphasize that extraordinary claims require extraordinary evidence. They point out that Loeb's ideas, while stimulating, do not yet have direct observational support. The nickel-to-iron ratio, for example, is intriguing but not conclusive. Natural processes in distant star systems could produce unusual chemical compositions that we simply haven't encountered before. Similarly, the comet's speed and size, while record-breaking, might fall within the extreme end of a natural distribution once more data are collected. To illustrate this, some astronomers have drawn parallels with the history of exoplanet discoveries. When the first hot Jupiters were found, giant planets orbiting very close to their stars, they seemed to defy all expectations. Early models of planetary formation didn't predict such systems. For a time, these planets were seen as strange outliers. But as more data accumulated, it became clear that hot Jupiters were simply a common type of planet that our early models had failed to anticipate. What was once an anomaly became a new normal. Similarly, 3I Atlas might seem extraordinary today, but future discoveries could place it neatly within a broader context. Another statistical challenge lies in understanding how often interstellar objects should visit our solar system. Based on existing models, astronomers expected to detect perhaps one interstellar object every few years with current technology. The fact that 3 significant objects have been observed within less than a decade has prompted some to revisit those estimates. Perhaps the density of such objects in the galaxy is higher than previously assumed, or perhaps our detection capabilities have improved faster than expected. Either way, 3I Atlas is forcing a recalibration of expectations. The comet's extreme eccentricity also plays a role in these debates. With an eccentricity of 6.2, 3I Atlas is on a trajectory that is not just hyperbolic, but extremely so. This value far exceeds anything typical for solar system comets, whose eccentricities usually hover around values just below or slightly above 1. The implications of such a high eccentricity are profound. It means that the comet is moving so fast that the Sun's gravity barely affects its course. For some scientists, this is a clue about its possible origin in powerful gravitational interactions elsewhere in the galaxy. For others, it is a reminder of just how diverse interstellar trajectories can be. Through all this, the scientific community maintains a healthy skepticism, not cynicism, but a careful insistence on evidence. This skepticism is not meant to dampen curiosity. It is what keeps science grounded. By testing bold ideas against hard data, scientists refine their understanding and avoid premature conclusions. In the case of 3I Atlas, this means carefully collecting observations, comparing them to models, and being willing to revise those models as new information emerges. There is also a cultural dimension to this debate. Loeb's technological speculations have attracted significant media attention, sometimes overshadowing the quieter, more methodical work of other researchers. Some scientists worry that sensational headlines might distort public understanding, creating the impression that the artificial hypothesis is more widely accepted than it really is. Others see this as an opportunity. Even if the alien technology angle remains unproven, the excitement it generates draws attention to the broader field of interstellar astronomy, inspiring new generations of scientists to get involved. Ultimately, the criticisms and statistical discussions surrounding 3I Atlas are not signs of disagreement so much as signs of a healthy, vibrant scientific process. Different perspectives clash, evidence is scrutinized, and over time, a clearer picture will emerge. Whether the comet turns out to be a perfectly natural but unusual object or something that forces us to rewrite parts of our cosmic story, the process of discovery is unfolding exactly as it should, slowly, carefully, and with an open but critical mind. As the comet continues its journey, indifferent to these debates, it leaves behind a trail not only of gas and dust but of questions that stretch across disciplines, from astrophysics to philosophy. And in those questions, humanity finds its greatest strength, the ability to wonder, to argue, to explore, and to learn. The debates about 3I Atlas are not simply academic exercises. They reveal how science functions as a living, evolving conversation. Each new piece of data enters a complex network of interpretations, models, and prior discoveries. Some researchers say the comet has, in a sense, become a kind of cosmic Rorschach test, its strange characteristics reflecting not only the mysteries of interstellar space but also the diverse intellectual landscapes of those who study it. One of the central challenges lies in interpreting incomplete data. Despite advances in observational technology, our view of 3I Atlas remains limited. It is a distant object, racing through space at extraordinary speed. Most of our knowledge comes from brief observational windows when it is visible through powerful telescopes, and even then, the signals are faint. Scientists must extract meaning from tiny variations in light, from the subtle fingerprints of elements in its spectrum, and from the precise tracing of its path through the solar system. These kinds of measurements are inherently difficult, and they come with uncertainties. Every data point is accompanied by margins of error. These uncertainties are not signs of weakness. They are essential components of honest science. By acknowledging what we don't know, scientists can build more reliable models and avoid the trap of overconfidence. With 3I Atlas, the uncertainties are larger than usual simply because the object is so unusual. Its speed, its distance, its composition, all push the limits of current observational techniques. This is why statistical reasoning becomes so important. For example, when scientists say that 3I Atlas has an eccentricity of 6.2, this is not a single, perfectly precise number carved into stone. It is a value derived from measurements, calculations, and models, all of which carry small uncertainties. Similarly, when researchers discuss how many interstellar objects should be detectable, they are not citing fixed truths but estimates based on incomplete data and evolving technology. As new telescopes come online and as methods improve, these estimates will shift. In recent years, the field of interstellar object statistics has grown rapidly. Before 2017, when Oumuamua was discovered, astronomers had no confirmed examples of objects passing through from outside the solar system. Theorists had predicted their existence, but without real detections, the estimates were vague. Oumuamua provided the first hard data point, and Borisov the second. Each discovery allowed scientists to refine their models of how often such objects should appear, what sizes they might have, and how fast they might travel. But 3I Atlas doesn't fit neatly into those early models. Its combination of size, speed, and chemical peculiarities places it near the edges of predicted distributions, or perhaps beyond them. Some researchers argue that this indicates our models were simply too narrow, based on limited examples. Others believe it points to an unexpected population of interstellar bodies with different origins or ejection mechanisms. Either way, the comet is forcing a reevaluation of what we thought we knew. Another subtle issue is selection bias. Modern surveys are excellent at spotting certain kinds of objects, bright, large, or passing close to Earth, but less good at detecting small, faint, or distant ones. This means that our sample of interstellar objects may not be representative of the true population. Imagine trying to estimate the average size of fish in the ocean using only a net that can catch fish above a certain size. Naturally, your estimate would skew large. In the same way, early interstellar discoveries might be disproportionately fast and large because those are the ones we can currently see. Some scientists are excited by this prospect. If our current instruments are catching only the tip of the iceberg, then the galaxy may be teeming with countless small interstellar fragments, drifting silently through space. As technology improves, these objects could be detected more frequently, providing a far richer dataset. This would allow astronomers to build much more accurate statistical models, revealing patterns we can only guess at today. Others, however, see in 3I Atlas a genuine anomaly that challenges existing frameworks. For them, it is not just a question of improving technology but of confronting the possibility that something unexpected is happening out there in the galaxy. Perhaps some star systems produce unusually large and fast ejected bodies. Perhaps gravitational interactions in certain environments are more violent than previously modeled. Or perhaps, as some more adventurous theories suggest, there are processes we haven't even begun to imagine. Amid these debates, a remarkable thing is happening: collaboration. Astronomers from around the world are pooling their observations, sharing data, and comparing models. Amateur astronomers also play a role, sometimes contributing crucial measurements that help refine trajectories. Space agencies coordinate to ensure that major telescopes are pointed at the comet during key windows. The pursuit of knowledge about 3i Atlas has become a global effort, uniting people across languages, time zones, and cultures in the shared task of understanding a visitor from the stars. The statistical discussions often take place in quiet, meticulous settings: research papers, conferences, late-night coding sessions where scientists adjust models and rerun simulations. But behind these technical details lies something profoundly human: curiosity. The numbers are not just numbers, they are clues. Each data point is like a breadcrumb left on a vast cosmic trail, and somewhere down that trail lies a deeper understanding of how the galaxy works. The debate over 3i Atlas also highlights a healthy tension within science: the balance between skepticism and wonder. Some scientists emphasize sticking close to established explanations, wary of leaping to extraordinary conclusions without extraordinary evidence. Others argue that openness to the unexpected is essential, that revolutionary discoveries often begin as anomalies that didn't fit existing models. Both perspectives are necessary. Skepticism keeps us grounded, wonder keeps us reaching. And in this balance, 3i Atlas has found its place. It is a catalyst, a spark that pushes the scientific community to refine its tools, expand its models, and embrace the unknown. The comet itself doesn't care about our debates. It follows its ancient trajectory through space, silent and unchanged. But for us, its passage is a moment of intellectual awakening, a reminder that the galaxy is not a solved puzzle, but a vast, ever-changing story still waiting to be read. Somewhere in the deep night, telescopes continue to track its faint light. Computers hum with calculations. Scientists discuss probabilities, outliers, and distributions. And beneath it all, there is the quiet thrill of knowing that we are witnessing something rare and extraordinary, a cosmic traveler that has crossed the interstellar gulf to briefly share our corner of the galaxy before vanishing back into the endless dark. This moment will pass, as all astronomical events do. But the data it leaves behind will be studied for years, shaping our understanding and perhaps preparing us for future visitors. The statistics will grow richer. The models will grow more precise. And maybe, just maybe, when the next mysterious object appears, we will be ready to understand it just a little better than before. Once the extraordinary nature of 3i Atlas became clear, a quiet urgency spread through the global astronomical community. This was no ordinary comet, no routine visitor looping gently around the sun. This was a fast, ancient traveler from the depths of interstellar space, moving so swiftly that it would offer only a brief window for observation before disappearing forever. For scientists, this was a once-in-a-lifetime opportunity, a cosmic guest who would stay for only a moment and then be gone for all eternity. It began with the discovery itself, when telescopes first detected the unusual trajectory and incredible speed of the comet. Within days, teams across the world were calculating its orbit, confirming that its eccentricity of 6.2 placed it firmly in the category of interstellar objects. As the news spread, research centers, observatories, and space agencies began adjusting their schedules. Telescopes that had been booked months in advance were suddenly retargeted. Instruments were recalibrated. Observing time was rearranged like a massive celestial chessboard, all to focus on this single mysterious visitor. NASA and ESA both recognized the significance immediately. These agencies maintain networks of ground-based telescopes, but more importantly, they control some of humanity's most powerful space observatories, tools that can peer deeper and more clearly than anything on Earth. The Hubble Space Telescope, despite its age, remains one of the most reliable instruments for high-resolution imaging of distant objects. Meanwhile, the James Webb Space Telescope, with its extraordinary infrared sensitivity, can analyze the chemical composition of a comet's coma and tail with unprecedented precision. Within weeks of the comet's discovery, both telescopes were pointed toward 3i Atlas. Hubble captured stunning images of its diffuse tail stretching into space, revealing subtle structures that hinted at complex outgassing patterns. Webb's instruments collected spectra that showed not only water vapor and carbon compounds but also unexpected traces of nickel and iron, elements that deepened the mystery rather than solving it. Each observation added more data to a rapidly growing scientific archive, creating a kind of time capsule that future generations of astronomers will study long after the comet itself has vanished into the dark. But it wasn't just the big space telescopes that joined the hunt. Across Earth, a patchwork network of professional and amateur observatories came alive with activity. From the deserts of Chile to the mountains of Hawaii, from European observatories to small backyard telescopes, astronomers pointed their instruments skyward. Every observation mattered. Even a few minutes of data from a modest telescope could help refine the comet's trajectory, improve models of its rotation, or catch subtle changes in its brightness. Coordinating these efforts required remarkable collaboration. Space agencies set up special data-sharing portals so that information could flow quickly between teams. Observers around the world synchronized their measurements, creating continuous monitoring that followed the comet as Earth turned beneath the stars. It was a kind of global relay race, with one observatory handing off to the next as night fell across different continents. The sense of shared purpose was palpable. For a brief period, the competitive edges that sometimes color scientific research faded away, replaced by a collective determination to learn as much as possible from this fleeting event. Teams that might normally be rivals shared their raw data, knowing that time was too short for anyone to work in isolation. The comet was moving too quickly. The window for meaningful observation would close in months, not years. Among the most ambitious observations came from instruments orbiting Mars. Several spacecraft in Martian orbit, equipped with cameras and spectrometers for studying the planet's atmosphere and surface, were redirected to observe the comet as it passed through regions of the sky invisible from Earth. This provided unique vantage points, allowing astronomers to build three-dimensional models of the comet's coma and tail. It was the first time such a coordinated Earth-Mars observation campaign had been attempted for an interstellar object, and it set a precedent for future events. Meanwhile, radar facilities on Earth, such as the Goldstone Solar System radar, attempted to bounce signals off the comet to measure its size, shape, and surface properties. Radar observations are notoriously difficult for faint, distant targets, especially objects moving as fast as 3i Atlas. But even a partial radar echo could yield precious information about its structure. These efforts pushed the limits of current technology, sometimes producing ambiguous results, but they represented humanity's determination to use every available tool to study this enigmatic traveler. The campaign was not without challenges. Observing an object like 3i Atlas is complicated by its speed and trajectory. It moves quickly across the sky, demanding precise tracking that tests the capabilities of telescope mounts and software. Its brightness can fluctuate unpredictably as sunlight strikes different regions, causing outbursts of gas and dust. And because it spends part of its journey near the sun from Earth's perspective, there are periods when it is too close to the sun's glare to observe safely. Astronomers had to plan around these obstacles, seizing every clear night and every favorable angle. Despite these hurdles, the amount of data collected has been extraordinary. Already, scientists have compiled terabytes of observations, light curves, spectra, images, radar echoes, and more. This wealth of information will take years to fully analyze. Researchers are building models to simulate the comet's structure, its possible origins, and its interactions with solar radiation. Each dataset is like a puzzle piece, and when combined, they will eventually reveal a clearer picture of what 3i Atlas truly is. For many astronomers, this global effort has been deeply inspiring. It demonstrates what humanity can achieve when curiosity becomes a shared mission. No single telescope, no single team, could have captured all this information alone. But together, across continents and orbits, we have woven a tapestry of knowledge around a fleeting point of light racing through the cosmos. And somewhere, far from all this activity, the comet itself continues its silent journey. It does not know it is being watched, does not care about the networks of telescopes and computers trained upon it. It simply moves along the trajectory set billions of years ago, indifferent to our fascination. Yet in watching it, in chasing its faint light across the heavens, we are reminded of something profound, that even the briefest encounters with the unknown can unite us in wonder. As the great global observing campaign gathered momentum, a new phase of the comet's journey unfolded. By late October, 3I Atlas approached its perihelion, the closest point to the Sun along its hyperbolic trajectory. This moment had been anticipated for months, carefully calculated by astronomers using every scrap of positional data they had gathered. On October 29th, the comet reached that turning point, swooping past the inner solar system in a silent arc at breathtaking speed. From Earth, however, most observers could not witness this dramatic moment directly. When a comet nears the Sun, it often becomes lost in the overwhelming glare of daylight. Even the most sensitive telescopes are forced to wait, their instruments carefully protected from accidental exposure to the Sun's blinding light. For 3I Atlas, this period of solar conjunction effectively marked a temporary disappearance from our skies. It slipped behind the Sun's brilliance, hidden from view like a traveler vanishing into a blinding sunrise. This brief disappearance is not unexpected. Many comets, even those bound to the solar system, follow orbits that carry them behind the Sun from Earth's perspective. Observers simply mark their calendars, waiting patiently for the moment when the comet reemerges on the other side. In the case of 3I Atlas, astronomers have predicted that this will happen in early December 2025. As Earth continues its steady orbit, and the comet races outward along its hyperbolic path, their relative positions will shift. Eventually, the geometry will align so that the comet will become visible once more in the pre-dawn sky. This upcoming window of visibility has generated a quiet, growing excitement within the astronomical community. Unlike its approach, which caught many by surprise, this second act has been carefully planned. Telescopes are already scheduled, instruments are prepared, and amateur observers around the world are eagerly awaiting their chance to point their lenses toward the returning visitor. For some, this will be the first opportunity to see it for themselves. For others, it will be a chance to collect follow-up data that will complement the intense observing campaigns from earlier in the year. The comet's reappearance will be more than just a scientific event. It will also be a moment of beauty. In early December, before the Sun climbs too high, 3I Atlas will gradually emerge against the dark velvet of the morning sky. Depending on its brightness at that time, it may be visible through binoculars or small telescopes, possibly even to the naked eye under exceptionally dark skies. Observers who rise early and travel away from city lights may be rewarded with the sight of a faint, ghostly streak, an interstellar traveler briefly gracing our skies one last time before vanishing forever. For comet watchers, these moments are precious. Unlike periodic comets that return again and again, 3I Atlas will never come back. Its orbit is not elliptical but hyperbolic, meaning that it is on a one-way journey out of the solar system. Once it leaves our cosmic neighborhood, it will continue into interstellar space, drifting for billions of years through the vastness between the stars. There will be no second chance. This December represents the final opportunity for humanity to look upon this ancient object with our own eyes. Astronomers are preparing meticulously for this moment. Because the comet is moving so quickly, predicting its exact brightness and position is challenging. Its activity level may change as it moves farther from the Sun, perhaps fading rapidly or surprising observers with unexpected outbursts. To make the most of the narrow observing window, researchers are relying on sophisticated computer models that simulate the comet's behavior under various scenarios. These models incorporate data from earlier observations, including measurements of outgassing, rotation, and surface composition, to forecast what the comet might do next. Some teams are even planning coordinated global observations similar to those conducted during its approach. By synchronizing observations from multiple locations around the world, astronomers hope to build continuous light curves that will reveal how the comet evolves as it recedes. This will allow them to track any sudden changes in activity, measure how its tail structure shifts, and refine calculations of its trajectory with remarkable precision. For amateur astronomers, the comet's December return represents a thrilling challenge. Tracking a faint, fast-moving object requires patience, skill, and often a bit of luck with the weather. Many are already sharing tips and strategies online, discussing which filters work best, what times of night offer the clearest views, and how to photograph the comet without overexposing the delicate structure of its tail. Some are organizing local comet mornings, small gatherings where enthusiasts can share telescopes and experience the event together. In a way, 3i Atlas is bringing people together across continents, uniting both professionals and hobbyists in a shared moment of cosmic wonder. Meanwhile, spacecraft continue to watch from perspectives unavailable to ground-based observers. Some orbiters around these different vantage points will provide valuable complementary data, helping astronomers understand how the comet's coma and tail respond as solar radiation changes with distance. It's a three-dimensional puzzle, and each observing platform provides another piece. As December approaches, a sense of bittersweet anticipation grows. Everyone involved in the study of 3i Atlas knows that this is the final curtain call. After this, the comet will accelerate outward, fading into the darkness as it leaves the sun's gravitational influence behind. No spacecraft will follow it, no telescope will be able to track it forever. It will simply become another faint, distant object, catalogued and remembered but no longer visible. And yet, this farewell moment is part of what makes its story so moving. We are witnessing not just an astronomical event but a passage, a crossing of paths between humanity and a traveler from another star system. For a few brief months, our worlds have intersected. We have observed, measured, speculated, and wondered. And soon as it departs, we will be left with memories, data, and the lingering sense that we have touched something ancient and unknowable. In early December's quiet mornings, when the air is cold and still and the stars shine brightest, those who step outside to look for 3i Atlas will become part of this shared story. Whether they see it through the eyepiece of a telescope or glimpse it faintly with the naked eye, they will be connecting with a traveler that began its journey long before our solar system even formed. That realization alone is enough to send a shiver down the spine, not of fear, but of awe. As the journey of Comet 3i Atlas through our skies nears its end, a quiet sense of wonder lingers in the air. We have followed this ancient traveler from the moment it burst into our solar system at unimaginable speed, through the mysteries of its composition, the theories about its origins, the unprecedented efforts to observe it, and the anticipation of its farewell appearance. It has been a story both scientific and poetic, blending hard data with the timeless feeling of looking up at the night sky and knowing that something extraordinary is happening out there, far beyond the boundaries of our world. Now, as we stand beneath the stars, one simple but profound question remains: what is really driving this celestial bullet through space? Is it purely the product of natural cosmic forces, the gravitational slingshots of giant planets, the turbulent birthplaces of stars, the ancient collisions and ejections that shaped our galaxy? Or could there be something more, something that hints at technology, intelligence, or forces we have yet to comprehend? The debate over the nature of 3i Atlas has stirred imaginations around the world. Some scientists see it as a time capsule from the early days of the Milky Way, a fragment of distant star systems flung outward billions of years ago, carrying with it the chemical fingerprints of its long-lost home. Others, like Avi Loeb, are willing to ask more radical questions. Could such an object, with its unusual composition and extreme speed, be evidence of something artificial? Could it be debris from a long-vanished civilization, or even a probe designed to drift silently through interstellar space, waiting to be noticed? These ideas might sound like science fiction, but they are part of what makes astronomy so endlessly captivating. The universe is vast and full of surprises, and history has shown that our understanding is always evolving. What seems impossible today may become obvious tomorrow. And somewhere, in that space between certainty and curiosity, lies the true heart of discovery. For now, 3i Atlas remains a mystery. We have gathered data, analyzed spectra, measured trajectories, and constructed theories, but the full story of this visitor will unfold slowly, over years of careful study. Scientists will pore over the information collected during its brief time near the Sun, searching for patterns and clues. Perhaps one day, new insights will emerge, an unexpected detail in the chemical makeup, a subtle feature in the trajectory, a clue hidden in plain sight, that will illuminate its origins once and for all. But beyond the scientific quest, there is something deeply human in our reaction to this comet. We are drawn to stories of travelers, of unexpected arrivals, of messengers from afar. 3i Atlas has given us a chance to feel that sense of connection to the wider cosmos. For a fleeting moment, it has reminded us that we are part of something immense and ancient. That the space beyond our atmosphere is not empty, but alive with movement, history, and wonder. Imagine standing outside on a quiet December morning, far from city lights, your breath clouding in the cold air. The stars overhead are sharp and clear, and somewhere near the horizon, you glimpse a faint, silvery streak. That light has traveled across unimaginable distances, carrying with it the story of another time and place. As you look at it, you become part of that story too. You are witnessing a moment that will never come again. This is why the tale of 3i Atlas matters. It's not just about orbital mechanics or spectral analysis. It's about curiosity, unity, and the shared experience of wonder. Scientists, amateur astronomers, and casual stargazers alike have all turned their attention to this visitor. For a few short months, we have been united by a single point of light in the sky, asking the same questions, feeling the same sense of awe. And so, as this story draws to a close, we pass the question on to you. What do you think is driving this comet on its incredible journey? Is it the relentless force of natural cosmic dynamics, or could there be a deeper mystery waiting to be uncovered? Your thoughts, your imagination, and your curiosity are part of this conversation. Share your ideas, your wonder, and your perspective. This is not just a story told by scientists in observatories. It's a story told by all of us who look up at the night sky and dare to wonder. The universe invites participation. It asks us to be curious, to dream, and to explore. And who knows, perhaps in your thoughts and questions lies the spark of the next great discovery. If you've enjoyed this journey through the mysteries of 3i Atlas, consider joining us as we continue to explore the cosmos together. Subscribe to stay up to date with the latest astronomical events, from the storms of Jupiter to the shifting sands of Mars. In the years ahead, new discoveries await, some predictable, others completely unexpected. Together, we can witness them, question them, and keep that flame of curiosity alive. For now, though, let's take a final moment to reflect. Somewhere, even as you listen to these words, 3i Atlas is already far from the Sun, speeding away into the darkness between the stars. It does not slow down, it does not look back. Its path is set, a trajectory written billions of years ago. It will pass beyond the reach of our telescopes, and then beyond the reach of our imagination, continuing its endless voyage through the galaxy. But we will remember it. Not just as a comet with unusual speed and mysterious metals, but as a reminder of the vastness of the universe and the fleeting beauty of encounters with the unknown. 3i Atlas has come and gone, but the sense of wonder it inspired will remain. Look up at the sky tonight, and think of that traveler. Somewhere out there, beyond the thin shell of our atmosphere, beyond the orbit of the outer planets, it continues its journey. And we, here on our tiny world, continue ours. For a moment, our paths crossed. And that, in itself, is something extraordinary. The night sky has always been a canvas for our imagination. Long before telescopes, satellites, or spacecraft, people stood beneath the stars and wondered what lay beyond. They told stories of gods and heroes, of signs and omens, of distant fires that shaped the destiny of worlds. But now, with the tools of modern science, we find ourselves doing something remarkably similar, still looking up, still asking questions, still weaving stories around the lights that move through the darkness. The difference is that today, some of those lights are no longer just stars. Some are travelers, like 3i Atlas, crossing through our cosmic neighborhood for reasons that stretch back to the dawn of the galaxy itself. As this comet speeds away, there's something strangely comforting in knowing that it will continue its journey long after we are gone. Long after our telescopes have gone silent. Long after our cities have changed. Long after we ourselves have become part of history, this ancient traveler will still be drifting through the deep, silent night between stars. It is a reminder of time on a scale we rarely consider, a timeline not measured in human lives or civilizations, but in billions of years, in galactic revolutions, in the slow rhythm of the cosmos. Somewhere, perhaps tens of thousands of years from now, 3i Atlas will pass near another star. Maybe it will glide through another planetary system, briefly illuminated by the light of a new sun. Perhaps intelligent beings on a distant world will detect it, study its path, and wonder where it came from. They might build their own theories, their own stories, just as we have. They may even ask themselves whether this visitor carries clues about distant civilizations, about the formation of other galaxies, about the shared history of the universe. And they will never know that, once upon a time, far away, we too watched it pass. Interstellar objects like this remind us that the universe is not static. It is alive with motion, filled with wanderers that have no allegiance to any single star. Comets, asteroids, fragments of ancient worlds, all drifting through the galaxy like messages in bottles tossed into a cosmic ocean. Some travel for eons before encountering another world. Some may never be seen by any form of life. But each one is a record of history written in ice, rock, and dust. Each one carries a story, waiting for someone curious enough to read it. And this raises a fascinating possibility for our own future. One day, humanity may be able to send missions to intercept objects like 3i Atlas as they pass through our solar system. These would be spacecraft capable of rapid acceleration, catching up to these cosmic bullets, studying them up close, perhaps even collecting samples before they disappear forever. There are already early concepts being discussed, nimble, autonomous probes that could be launched on short notice, designed to chase down interstellar objects and give us a direct glimpse into material from other star systems. Imagine what we could learn if we held a piece of such a traveler in our hands, alien ices, untouched since the birth of distant suns. Even now, astronomers and engineers are thinking ahead to the next visitor. 3i Atlas is not the first, and it will not be the last. Oumuamua came before, mysterious and swift, and others will follow. The more carefully we watch the sky, the better our chances of spotting these travelers early, giving us time to prepare, to observe, and maybe, someday, to meet them up close. Future generations may look back on this moment as the beginning of a new chapter in exploration, the era when humanity first began to study not only our solar system but also the messengers drifting in from the stars beyond. And perhaps, in some far-off future, our own technology will send objects like this into the galaxy. Probes might drift between star systems, carrying information, exploring quietly, waiting to be discovered. Our descendants could become the architects of the next generation of interstellar wanderers. And somewhere, millions or billions of years from now, beings under another sky might look up, see a faint light in the darkness, and wonder about us. The story would continue, written across light years and epochs. But even if we set aside all the distant possibilities, there's something profoundly beautiful about the present moment. Right now, in this brief intersection of paths, we have witnessed a traveler that connects the unimaginable past with the unimaginable future. We have looked at it through our instruments, studied it with our minds, and felt something stir in our hearts. Ah, curiosity. A quiet sense of belonging to a universe that is vast beyond measure, and yet capable of bringing distant objects close enough for us to see, even if only for a heartbeat of cosmic time. Think of the billions of years this comet has wandered, untouched, unobserved, passing through regions of space so dark and empty that not even starlight could warm its icy core. And now, for a few short months, it has been bathed in sunlight, seen by telescopes, whispered about in observatories, imagined by countless minds. In a way, 3i Atlas has briefly become part of our story, and we have become part of its. This is the quiet power of astronomy. It does not shout. It does not demand. It simply invites us to look, to wonder, and to remember that we are participants in something far larger than ourselves. The stars do not change for us, but we change when we look at them. The comets do not alter their paths for our sake, but our understanding deepens when we trace their journeys. Through these encounters, fleeting as they are, we rediscover a sense of humility and connection that is easy to lose in the noise of daily life. So tonight, if the sky is clear, step outside. Let your eyes adjust to the darkness. Find a quiet spot where the stars are bright. Think of the traveler racing away into the cosmic sea. Think of the countless others still out there, waiting to be discovered. And think of yourself, a being on a small planet, aware enough to notice, curious enough to care, part of a lineage that has always looked upward. 3i Atlas will be gone soon, but the sky will remain. And in that sky, future wonders are waiting. All we have to do is keep looking, keep wondering, and keep listening to the stories the universe whispers through the stars.